Alright, so in this video we're going to look at the concept of period, velocity, and acceleration as a function of time. So I mentioned earlier that simple harmonic motion is motion when you can describe the oscillation using a sine or cosine function. So we're going to start here with the idea that our position here, so x in our oscillation, a is going to be the radius of the circle, can be represented with the concept where x is equal to a cosine of theta. So this is theta in here. Now, given that earlier in the semester we learned that omega, so angular velocity, now that we're calling angular frequency, is equal to theta divided by t, we can sub that in so that x is equal to a cosine of our angular frequency times time. Sometimes you'll see this written with a phase angle in it, taking it into account the idea that you might not start at x equals 0 initially. But we're going to worry about this relationship up here. We're going to assume we're always going to start with our cosine of 0 equaling 1, rather than having x start at someplace other than it's at our position right here. Alright, so we know we've written down the idea of position as a function of time. Now, when we want to know velocity, well, we know that velocity is equal to the first derivative of our position function. So what I'm going to do here is I'm going to take the first derivative of our position function, and that's going to give me a negative a frequency sine now of omega t. It's a little bit too squished. Let's try writing that a little bit bigger. So now when we go to do this, rather than starting at our maximum value here, we're going to start at 0. And that's because we're looking at a sine curve, and since it's negative I'm going to go down, rather than a cosine curve. And this makes sense due to the conservation of energy, because we know that whenever we're at x equals a, or our amplitude, velocity is equal to 0, and this comes out of the conservation of energy. Where our maximum velocity here is going to be the amplitude times our angular velocity. So this point right here would be a omega. So the last thing we want to do here is we know that acceleration is equal to the first derivative of the velocity function. So I can take the derivative again here, and we get acceleration, or not acceleration, amplitude times angular frequency squared times back now to the cosine of omega t, and this is still negative. Let me erase that again, since I'm trying to write here a little bit squished. Alright, so now, once again, we're back to a cosine curve, so we expect our maximum acceleration to occur at the same place as our maximum position. Only this time we're going to start negative, because acceleration is going to be negative. So we're still doing a cosine curve, but it's sort of the mirror of the position, because instead of starting positive, it's negative, because the force that we're looking at is a restoring force. So this position here would be amplitude times angular frequency squared. So that would be your maximum acceleration. So the idea here is that your maximum value for your position is your amplitude, and then cosine goes from -1 to +1. So whatever your amplitude is times the decimal that comes from taking the cosine of the angle given by omega t gives you your position. Same thing with velocity. Your maximum velocity is your amplitude times your angular frequency. Sine also goes from 1 to -1. So whatever omega t gives you whatever fraction of the maximum velocity that you're at. And last thing with acceleration. So your cosine function once again goes from 1 to -1. So you're going to get some fraction of whatever your maximum acceleration is based upon what omega t is. And remember, omega t comes from our relationship for angular velocity, that angular velocity is theta over t. Alright, and also note here, this shows us how these are out of phase. So your max position and your max acceleration occurs at the same spot in the motion, but your velocity is out of sync. Where it's going to be 0 where everything else is at their max. Pay special attention to this section because this is one of the few places that I do calculus in this particular unit. So it is highly likely to appear on the exam as a calculus question.